Hello and welcome to another video. In this video we're going to be working on maximum difference between node and ancestor. And in the problem you're given the root of a binary tree and you want to return the maximum difference between any two ancestors. So ancestor just means nodes on the same root to leaf path. So for example, here's a path and all of these nodes are ancestors. And similarly, this node and this node are not, because it has to be a root to leaf path like this or like this or like this. So in this problem, the answer is this 8 minus 1 here. So you would get 7. That's the biggest difference you can make. And let's take a look at this one. So in this problem, everything in this is an ancestor because there's just this path here. So the difference here is just going to be 3 because it's going to be these two nodes. So that's basically what we need to do. Let's have a tree, and we basically need to figure out the biggest difference between two nodes on a root to leaf path. So let's kind of walk through this one. And basically, there's a few ways to do this. And one thing you could do that makes these problems a lot easier is you could make a variable outside of a traversal like DFS function. So you could just make a result variable. And if you're trying to maximize it, set it equal to negative infinity or something. And then have your traverse function. And then in your traverse or DFS or whatever you want to call it, then you can modify this result to be the maximum of the result and some current thing. And that helps a lot because then you don't have to figure out what to return. So you can just return nothing and modify it there. But I'll show you one way you could do it. And this is kind of open-ended. There's a bunch of ways as long as you kind of know what you want to do. So basically, you're going to know that on a single path, you only need to really store the maximum and minimum value. Because let's just take these nodes here. Let's say we have this path like this. The biggest difference is always going to be the biggest value minus the smallest value, right? So we only need to really store the 8 and the 3 or whatever we go down. Let's say we're going down here and we have some values. We only need to store the 8 and the 5 as we go down because the 7 is going to be completely useless. We basically just want to keep the biggest and smallest value encountered in our path because those are going to be the only ones necessary to get the best result. So let's have a result there. Actually, we'll have some returned output. So basically what we're going to do is we're going to do a DFS. So we'll start here. We'll just pass in the beginning, we only have just this root value. So we'll just pass in this function with these two values. So we'll call this function on this node and we'll call it with these two values, right? 8 and 8. And then we will go left and we will go right. So when we go left, we want to compare the node to the values passed in. Obviously with the root, it's the same. So we don't really need to do anything. So we just go left. So we're going to go left with the value 8 and 8. Now we want to compare this node with the values passed in, and we want to figure out is it better than the maximum value or is it better than the minimum value or is it just completely useless? So the maximum value is going to be on the right, the minimum value is going to be on the left. And so it's obviously not better than the maximum because it's smaller, but it's better than the minimum, right? It's smaller. So we will adjust this new thing that we're passing down now to 7, 8. So we'll pass that down to both of its children. And now we do the same thing here. So is it better than the maximum? No, but it is better than the minimum. It's smaller than the minimum. So we will pass down the appropriate stuff here. So we will pass down 5, 8. And we will pass down 5, 8 here. And similarly here, we will also pass down 5, 8. So I'm just going to write 1 here. Actually, I could probably fit it. So 5, 8. I just won't have the parentheses, I guess. That'll make it smaller. And 5, 8. Okay. Now, basically, when a node has no more children, we can still pass down this best value. So we're actually going to take this 3 and do the same thing. Is it better than the 5, 8? Yes, it is. So we're actually going to pass this down to its null values. And then when the values are null, we can just still return the biggest minus the smallest value. So we'll basically pass down, because 3 is better than 5, we will pass down 3, 8 down here to its left null child. Same thing to the right null child. They'll return exactly the same thing. And then we will do the same thing over here. So we will pass down, is 1 better? Yes, it is. So we're going to pass down 1, 8 here. And same thing here, 2, 8. And 9 is actually better than the 8 on the higher one, and it's not better than the 5. So we'll pass down 5, 9 here. So now all of these are at null nodes, and we're going to pass this down to the left and right child, and they will return the exact same thing, right? So you return this to the left null node and the right null node, and we'll just say like if the node is null, then we can just return the biggest value minus the smallest value. So we can have this in another color. So we will return 5 up here, and we will return 7 over here. Then over here we will return 6. And over here we will return 4. Then basically for the nodes that we have, right, like we return 5 up here, we return 7 up here, and this is the value we're going to be returning. So we return this up here, because this has 2 null nodes, both of these values will return 5, both of these values will return 7, both of these will return 6, both of these will return 4, and so on. So now we're going to recurse up here with this return value of 5. So we're going to return 5 up here, and we're going to return 7 up here. And then we just need to check like which one is better, right? And that's the one we'll return. So 7 is bigger, so that's the one we'll return. So we'll return 7 up here. And similarly on this side, we're going to return 6 up here, and 4 up this way. And which one is better? 6 is better, so we'll return 6 up here. And then finally, which one is better, 7 and 6? It's 7, so we'll return 7 up here. And now this left side is exactly the same, so we can go through that. So we do the same thing. We pass down 8 and 8. Then the 9 is better than the 8, so we'll pass down 8, 9 to both of its children. So 8, 9. And I'll just not use the parentheses for the other part just to take up less space. So 2 is better than the 8, so we'll pass down 2, 9 here, and 2, 9 here. And here it's going to be 5, 9, and 5, 9. Then all of these have null nodes, so we have to pass down something to them as well. So 2, 9 is going to be exactly the same, right? So we'll just pass down 2, 9. Here, the 11 is better than the 9, so we'll pass down 2, 11. So we'll have commas still just so you can see the difference. Okay, and then here 1 is better than the 5, so we'll pass down 1, 9. And finally, 7 is not better than any of these. It doesn't make the smallest smaller or the biggest bigger, so this will just be 5, 9. So now same thing. These nodes are null, so we will just return the difference between these two values. So here we will return 7. And here we will return 9. Here we will return 8. And here we will return 4. Then we just return the better one of the two values to each one. So 9 is better, so we'll return 9 up here. Here 8 is better, so we'll return 8 up here. 9 is better here. And finally, we have 9 or 7, so 9 is better. So we found something with a difference of 9 somewhere. So let's take a look where that is, and it's going to be these two nodes over here, right? This is the best. And so that's pretty much all you do. So you just pass down the current smallest and biggest value, and as you have your current value, see, is it smaller than the smallest? Okay, I'll update the smallest. Is it bigger than the biggest? Okay, I'll update the biggest. Kind of messy, but that's pretty much what you do. And then you just return the difference between the smallest and the biggest. And if you have two different numbers, like if you have a left child and a right child, you just return the better one there. So you just take your two children, figure out which one has the bigger difference, and return that one. And if it has two null children, those two null children will return the exact same value. So now we can code it up. And like I said, there's a bunch of ways you can do this, but this is one of them. So we can make a traverse function or a DFS function. It's going to take a node, a small, and a big value. So if the node does not exist, remember, we want to still get this difference of the small and the big value. So we will just return big minus small. And then we will, if the nodes do exist, we want to modify our small and our big value to incorporate the node value. So we'll say small equals minimum of small and node value. And same thing for the big value. So big equals maximum of big and the node value. And then basically we just traverse left and right. So we'll say left equals DFS node.left, the updated small value and the updated big value, and same thing for right. Node.right, small, big. So now that we get these two values for the left and the right, we just return the bigger one of those because that's the bigger difference. So we just return max left, right. And like I said, if this is confusing to you, what you can do is you can just have a result variable up here. Don't even have a return at all. And then just in place, modify the result variable in this line. So say like result equals something, something. And you could totally do that if that makes more sense to you. So yeah, essentially now we just have to call this function. So we have to return traverse, and it's going to take the root. And as I showed in the picture, we just pass in the root value twice for the big and small value because that's when we first start with. So root.val, root.val. And we don't need this anymore. So we can run that. Let's see here. Oh, I think this should be called root. Yeah, so all these need to be called, actually, oh, it's because I called traverse instead of DFS. When I read it before, I had, let's see here, no.write small big, root val. Let's see what the error is now. Invalid syntax. Oh. Okay. Okay, there we go. And these are all going to be roughly the same. All these like tree traversals, you basically just traverse the tree once, whatever way you want. So they're all going to be like roughly the same speed. So the time here is going to be O of n, where n is the number of nodes, and the space is O of n because the same as always for trees, you have recursive stack frames. So if your tree looks like this, you're basically recursing all the way down, and you will have n recursive stack frames. So even though you're not like, even though you don't have a variable here, it's still the recursion depth is going to be O of n worst case. Yeah, and I think that's going to be all for this one. So not too bad of a problem. I think kind of easy. Just took a little while to draw the picture. But like I said, you could do this in a bunch of different ways. You can return a bunch of different things. But the main thing you have to realize is the best difference is always going to be the biggest value and the smallest value you've seen so far. Take those difference, and that's all you need. You don't need to like record the whole path or anything. And yeah, that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.